Hi everyone, I'm Dr. Samantha Kanza and I'm going to talk to you about using Semantic Web Technologies in scientific research. So firstly, I wanted to give you a bit of background about me. Many of you will probably know me as the coordinator of AI3SD, but I lead a double life. When I'm not coordinating the network, I also work on a number of different semantic web research projects. Confession time, I'm not a chemist. My background is in computer science and I fell in love with the semantic web back when I was an undergraduate. And when I came back to do my PhD, I wanted to find a domain to apply these technical skills to. I then discovered Professor Jeremy Frey and the work that he had done with Semantic Web Technologies and electronic lab notebooks, and I was absolutely hooked. I think there is so much potential in these technologies, and I want to share that with you today. So this presentation has four main components. Firstly, explaining what the semantic web is and describing its different technologies. Secondly, detailing the different affordances and use cases of semantic web technologies. Thirdly, talking about my own research on using semantic web technologies in scientific research. And finally, taking you through some of the key lessons I've learned through the various different projects I've worked on, including noting down some useful resources for chemists who might want to use semantic web technologies. So, number one, introducing semantic web technologies. So what is the semantic web? The semantic web was conceptualized by Sir Tim Berners-Lee, the man who invented the World Wide Web. The main goal of the semantic web was to create machine-readable data such that machines could better interpret information. Our language is really complex and words can have different meanings in different contexts. Humans are really good at picking up on context and meaning. We do it automatically without thinking. Take reading and reading as an example. You will just know which is which because of the context, but a computer won't. And semantic web provides a set of core standards to facilitate richer modeling of our data, such that we can provide this context and meaning. So therefore we can specify that we mean reading the city or reading the activity. The core data format of the semantic web is called Resource Description Framework, or RDF for short. This uses a graph model to store the data in triples of a subject, predicate, and object, whereby the predicate defines the relationship between the subject and the object. Triples can be linked together by making the object of one triple the subject of another, which enables us to break down data sets into this linked data format. I have put up a simplistic view of a triple on this page. The subject, predicate, and objects are often formed of persistent identifiers, aka a URI, which means that once you define a term, you can reuse that URI to refer to it again. So in this instance, a URI can be defined for specific drugs and diseases, and anyone who wants to refer to those specific things can reuse those URIs. You can have other things in your triples as well. They can be XSD data types, such as literals and integers, or you can have blank nodes. RDF supports storing data in this linked graph format, but it's not sufficient enough by itself to represent the required domain knowledge that provides the context and the meaning behind the data. In order to achieve this, we need ontologies. I do like to think of an ontology as essentially a fancy taxonomy with logic behind it. Or they can be thought of as controlled vocabularies or dictionaries, but essentially it all boils down to a similar description. Ontologies allow us to create formal definitions of the common terms used within a specific domain. They essentially allow us to describe the hierarchy of classes used to define the relationships and restrictions of different concepts within the ontology. By doing this, reusable terms can be built up for use within other systems that employ the same terminology. Ontologies are typically written in OWL, the web ontology language, as it has substantially more expressive capabilities, but simple ontologies can also be written in RDFS, which stands for RDF schema. So when we combine RDF with ontologies, we get knowledge graphs. There are a lot of fancy, slightly different definitions of knowledge graphs. One that I quite like is knowledge graphs are essentially graph network structures to describe real-world entities and their relationships through the combination of linked data and ontologies. And it's that combination of linked data and ontologies that is the key. If you want to turn a dataset into a knowledge graph, you need to have an ontology or set of ontologies to represent the required domain knowledge. And then you mark up the dataset in a linked data form using the objects and relationships defined in your ontologies. And then you essentially have a knowledge graph. We know that big companies like Google have their own knowledge graphs, and no doubt there are many companies creating what they might term as enhanced knowledge graphs, fancier knowledge graphs, and depending on the complexity and the reasoning of the ontologies you've used, obviously there will be different scopes for your knowledge graphs. but at their base form, it is that combination of RDF and ontologies. Ultimately, these graphs of linked entities have the potential to be really powerful structures, and researchers working on machine learning and AI have realized that using them can enable the application of advanced learning techniques on the data that can exploit the network of links. As noted in the previous slides, you can of course mark up your entire dataset in RDF to make it a fully linked dataset, but that might not always be what you want to do. You may just wish to annotate your documents with semantic metadata. There are 3 different formats for semantic annotation, and all of these can be embedded within HTML documents. And this will enable search engines such as Google to return more accurate, comprehensive results when indexing your websites. So now we have a data format and a way of defining the terms of our data. We need to be able to search it. Sparkle is a semantic web query language. It's based on SQL and has a similar structure of selecting, inserting, and deleting, except in a graph form rather than a tabular database form. The beauty of Sparkle is that it allows you to search on concepts, so you can add context to your search. As you can see from the query example on the screen, this query is searching for a laboratory that has a specific piece of equipment by defining the relationships that will need to be in place for a laboratory to fit the criteria of the query. So I'm now going to walk you through some of the affordances of the semantic web. The first one is defining a shared language, so you can be absolutely sure that you are talking about the same thing. Interestingly, I'm also leading an ethics working group looking at the unintended consequences of AI and digital collaboration in food. And one of the things we discovered early on was that when we were talking about terms that related to ethics and AI, even though we agreed in principle on the common terms that we needed to be thinking about, e.g. transparency, explainability, accessibility, we quickly realised that these words actually meant vastly different things across our different domains. In computer science, transparency could refer to whether algorithms are available and understandable, whereas in the food sector, it might refer to having access to information about the provenance of your food, for example. This really highlights the importance of defining your concepts and knowing whether you are talking about the same thing, as even the same words about the same topic, in this case ethics, can be defined really differently in different contexts and disciplines. So the next one is making your data machine readable. After all, if your computers can't understand your data, they aren't going to be able to do much with it. Making your data machine readable vastly opens up its potential to be used in different applications. One of the key comments that comes up at every single one of our workshops is the issue of data quality. Humans struggle with poor data quality, and so do machines. You wouldn't necessarily expect a human to effectively handle data of very poor quality, so we can't expect machines to either. The next one is rich, interoperable metadata. You can produce this data, which makes it much easier to search web pages and documents, and you can mark up text and know you're talking about the same thing. This can be really useful in applications such as electronic lab notebooks. You can mark up relevant terms to make searching and linking your documents together much easier. And there's linking data together. There are so often research questions that cannot be answered with a single data set, but combining these data sets together can allow you to find the undiscovered links. This can be really useful for domains such as drug discovery, where so often you need to link multiple data sets together to actually get a result. The next is inferencing. So we can add description logic to our ontologies, and we can set the domains and the ranges of relationships and set different restrictions on them, and then run a reasoner to see what new information can be inferred that wasn't explicitly defined in the data. A really simple example of this would be if we know that I, Sammy, am allergic to juniper, and if we know that gin has a botanical of juniper, then we can infer that I am allergic to gin. Thankfully, I'm not, by the way, or lockdown would have been a lot less bearable. But this can be really useful to infer extra knowledge that aren't explicitly defined in your data sets. Next is semantic search. As noted earlier, we can search on concepts rather than text, and then we can search through all the data sets that we have linked together. Sparkle can be used to make much more complex queries over these combined data sets to pull out new, previously unexplored connections. The final one is, I believe that semantics will play a really big part in allowing us to unlock the potential of AI and machine learning. We all know the saying garbage in, garbage out. It doesn't matter how beautiful your algorithm is. If you give it garbage data, you won't get any good results. Feeding your algorithm beautiful, semantically rich data has much greater potential. So that was just a bit of a whirlwind tour into the many use cases and affordances of the semantic web. There are lots of different applications for the semantic web, but I wanted to share with you my personal research work and the research work of the Frey Group into this area. Our main focus is how semantic web technologies can aid with the scientific research process, and particularly with respect to research data management. I would argue that we need semantics at every stage of the scientific research process, from planning through to publication. There is typically a wealth of data between a scientist's laboratory, lab notebooks, and their electronic data and write-ups, but they often remain really disconnected. I appreciate that we are still facing a barrier to more scientific research being digitised in the first place, but that doesn't mean we shouldn't be considering how to make the best use of this data once it's in an electronic form. So I'm going to talk to you about my different research projects that involve the use of semantic web technologies. I will focus mostly on the first three as they are more chemistry related, but I wanted to mention the agriculture and social science ones I've done as well, because they do feed into my lessons learned section. So the first project I'm going to talk to you about is my PhD research, which focused on digitising scientific research and semantically marking it up. The first half of my PhD was spent investigating electronic lab notebooks and trying to understand the current note-taking practice in the lab, and why, despite the overwhelming number of ELN offerings out there, why they still didn't seem popular. As a computer scientist, it seemed crazy to me that so much work was still conducted on paper, and I wanted to understand what the issues were and whether there were any viable solutions. It became clear quite quickly that this was not something that could just be fixed overnight, and was as much a human issue as a technology issue. There are still many barriers to using electronic lab notebooks, such as accessibility, hostile lab environments, ease of use, cost, data portability, compatibility, and of course the effort required to use them. However, despite these issues and the fact that we still have the real issue of scientists not wanting to digitize work that didn't work, which could be a whole new talk, but ultimately, despite all of this, some scientific research is being digitized. And whilst we obviously need to focus on increasing digitization, we also need to focus on providing a better environment for the work that is already digitized. So this line of investigation led me to the diagram on the right, which shows the breakdown of a layered semantic laboratory notebook. Through a thorough literature investigation and many interviews and focus groups with different scientists, and a combination of a bunch of different research studies conducted previously by the Frey Group in the eScience programme, this diagram shows the different functionality aspects that scientists would want to find in an electronic lab notebook. This has been broken down into 3 layers. So majority of the generic functionality desired, so secure backup, cloud access, generic notebooking features, can all be provided by a cloud notebook platform, which forms that notebook layer at the bottom. The second layer represents the domain-specific knowledge required that could be added onto this, rather than reinventing the wheel and creating the notebook part from scratch. The third layer, the semantic layer, details the knowledge management tools that are required. Semantic web technologies can be used to mark up the data with meaning and context to facilitate more intelligent searches and links. So this layered approach could be modularized to have different domain-based add-ons to different disciplines, and different ontologies could be used within the semantic layer. So a lot of the conversations I've had with scientists suggested that they are missing overall knowledge management. And as covered in the second part of my talk, using semantic web technologies gives a lot of affordances, such as facilitating links between related documents and ensuring that you are talking about the same thing, and searching over concepts rather than text. I think this semantic search aspect is really key, because that is objectively something a computer can do much better than a human. So that was the first half of my PhD, and having ascertained that a semantic layer approach could be useful, I wanted to investigate this in practice, as it's one thing for people to tell you what they want as an abstract concept, but without giving them something more tangible to consider, it's hard to move into a concrete approach. So I designed a rough web tool called Semanticat, which definitely stands for Semantic Catalog and has nothing whatsoever to do with my cat obsession. It is a tool to pull in documents and mark them up using some ontologies and a few different semantic tagging services, both generic and chemistry specific, to cover the requirements of tagging documents, linking to ontologies, and automatically recognizing chemicals that were all flagged up in the previous diagram. So this tool was used as a discussion tool in my focus groups to try and understand what scientists actually wanted from semantic tagging and searching. And the results were really interesting. Firstly, the ELNs are still primarily perceived as a replacement for, rather than a supplement to, a paper lab notebook. This is important because we need to understand the different problems and stages at stake here. Getting scientists to digitize their work in the first place is one issue, However, managing your research once it's in an electronic form is a different matter. And a reluctance to use ELNs isn't necessarily a reluctance to engage with technology, especially once your work is already in an electronic form. As noted in my previous slide, many scientists feel like they are missing out on good knowledge management. So even though they don't necessarily want to use an ELN, that doesn't mean they don't want tools to make their knowledge management easier. Therefore, in some instances, it might be that having a standalone semantic layer to help with knowledge management, linking between related documents, tagging and marking up, etc., might be much more useful than it always needing to be part of the formal ELN. Another key finding was it became very obvious that tagging and searching through a scientist's work is a very personal endeavour. This is not surprising in that we know that note-taking in itself is also very personal, but this does suggest that a one-size-fits-all approach won't work. Tagging and searching offerings need to be customizable. However, obviously there also needs to be a level of automation, as asking the scientists to do it all themselves also probably won't work. So potentially you need an offering where most of the tagging can be automated, but there'll be options for correction and customization, ideally with a technology that can learn from these changes. So finally, there was feedback that potentially some tags and annotations might be more useful for reading others' work rather than your own. The chances are you know your own work really well, but might want further information from someone else's. But obviously you still want that underlying metadata to be there for searching and linking. Obviously, there are a lot more findings with relation to the overall studies, but these are the key ones related to the Semantic Web Technologies. I wanted to give a quick shout out to another project I've been working on, which is the SEED project with the Pistoria Alliance. SEED stands for Semantic Enrichment of ELN Data, and obviously I jumped at the chance to get involved in this project, and this very much fits into my area of interest. So this project is also working towards producing a semantic layer for ELNs, and is now in its second phase, having done some initial mapping and ontology design work, and is actually looking at the kind of tools that can be used for this work. So another project I wanted to mention is the Talk to Lab project. So this is a Frey Group initiative and was worked on by my colleague, Dr. Nicola Knight, during her PhD. Talk to Lab is a prototype smart lab environment set up at a physics laser lab at the University of Southampton. We use sensors to monitor different aspects of the lab, currently temperature, water flow and laser power. And we can access this data via Alexas and interactive dashboards in the laboratory. This project is currently quite passive in terms of monitoring data, but we're really interested in progressing it further to make it a fully integrated smart laboratory that can be hooked up to health and safety data, inventory data, and of course a lab notebook. Semantic Web Technologies will be really useful here in helping us model our data consistently, and eventually we'd like to be able to link the system with a semantic layer so we can make more complex queries over our data. So I wanted to mention these two other projects briefly as well. As well, they're not chemistry related, my experience on them has definitely fed into the lessons learned section I'm going to cover next. So the Benchmark Scenario Planning Project was a joint project between Syngenta, the University of Southampton, the University of Aberystwyth and AGCO. The aim of the project was to model and cluster environmental and human factors related to crop yield to see which of the human factors could be tweaked to maximise crop yield based on your environmental situation. This is a typical case for the use of Semantic Web Technologies to model the data, as we had disparate data sets using different units and different classifications for our environmental data, and we wanted to be able to model them under a uniform classification to make comparisons. I won't go into loads of detail here due to time, but this project gave me lots of insights into modelling numerically based classification schemes within OWL, and unfortunately it showed that the current Semantic Web Toolkit isn't overly suitable for complex numerical data, which is something important to bear in mind when considering which technologies to use on a project. The social science project looked to model different social science data sets to explore health inequalities across different social classes. We had a number of different data sets to model and compare between, and some of these data sets were very large and decisions had to be made about which parts to model, and in some cases it wasn't complete. This gave some really interesting insight into how much harder it is to convert and model data sets with missing values. And we also had some really interesting discussions about where you need to make decisions to either directly model a data set or try and model the abstract concepts of a domain itself, depending on the requirements of the project. And also, more importantly, how the entire life cycle of the data modeling needs to be taken into account when you're designing your ontologies at the beginning, which is a lesson I'll be detailing in the next section. So on to the last segment of my talk. Here are some of the lessons I have learned throughout working on all of these different projects. I think Semantic Web Technologies have an amazing amount of potential as long as they're used productively. So hopefully the previous sections of my talk have given you some ideas about how Semantic Web Technologies can be used in different projects and scientific research, So now let's talk about how best to use them. The first lesson is reuse where possible and practical. There are lots of ontologies out there. Obviously, that doesn't necessarily mean that there will be one that covers what you are looking for, but it is worth checking to see if one does exist, or if one exists that partially covers what you want, in which case it's potentially worth making use of that and building on it. Or you could potentially use multiple ontologies depending on your use case. It's also worth noting that a lot of effort has gone into creating ontology design patterns, and it's worth familiarising yourself with these to see if they fit your criteria when you're creating your own ontologies. The second lesson is don't forget your standards. Just because RDF is a data standard, it doesn't mean it doesn't come with standards of its own. There are initiatives such as the Obo Foundry, which I'll mention in more detail later, that work on building standards and best practices for creating ontologies. Also, sometimes it can be really easy to get caught up in creating your own thing and forgetting that taxonomies and schemas, even if they aren't in a semantic form, do already exist. In addition to seeing if there are any ontologies that already exist for what you're looking to create, also look for existing taxonomies and schemas. Many domains already have specific ways of describing things that they've already defined, and it's worth considering that. Thirdly, think about why you are making your ontology and what your end use case is. Are you making it to mark up a specific data set? In which case, chances are you're probably going to need to at least custom build some of it yourself. Are you creating it as a domain standard without going as far as to using it to mark up data? If so, that's not necessarily an issue, but you do need to think really carefully about how people would use it and if it's viable for use. You need to think through that entire life cycle. Modularizing your ontologies is also really important. It can be tempting just to make a giant ontology of everything you need, but that's not ideal if it encompasses different information. Chunking them down into smaller ontologies of related terms means it is easier for those smaller ontologies to be reused in the future. Remember that fair is a 4-letter word. Yes, the I is really important, interoperable, obviously, but equally there's no point having beautiful semantic data if no one can find it, understand it, or reuse it. You need to play to Al's strengths. So this comes back to the BSP project lessons learned. Ontologies are great tools, but they aren't always the answer. For example, Al doesn't work particularly well with numerical-based classifications. There is a level of being able to add basic numeric restrictions to classes, but it's quite simplistic. And if you're looking to perform some fancy maths on your data, don't do it in your ontology. That doesn't mean you can't still use semantic web technologies effectively. It might just be that you have a linked data set, query on it, and do any necessary maths in a separate algorithm. But trying to incorporate all of the logic into your ontology design isn't always feasible. Next is think about what you want your data to look like and what you want to do with it. Are you looking to link your data set to others so you can query across multiple data sets, for example? If so, then yes, I imagine you would want to mark up the whole thing in RDF. Or are you just looking to add some richer metadata, in which case perhaps annotation would be better, or perhaps reducing some RDF as a separate metadata layer without marking up all the data underneath. It really depends on the data and your use case. When building an ontology, you need to think about what you want your data to look like at the end. Ultimately, if you're planning to fully mark up a data set and convert it all into triples, then you need to think about how they should look before creating the ontology. As once you start converting your data into a linked data format, you might find that it doesn't always pan out as you expect. You need to also consider how to handle certain aspects of your data. What if there's missing data? How are you going to deal with that? And how are you going to do your conversions? I would argue that there is still much progress to be made in the conversion process. There is a mapping language called R2RML which facilitates converting a database or CSV file into linked data. However, this doesn't work fantastically if you have missing data. Unfortunately, with the nature of the mapping language, there is an expectation that values will exist to be converted. There are some libraries that provide a level of flexibility around this conversion, but they still don't effectively handle what happens if you have an empty cell. There are tools that will do it for you, such as Linked Data Open Refine, or one I heard about recently in a different presentation called Web Karma, but they are still a bit clunky and involve a lot of additional work. You could just go old school and write a bash script, of course, although that requires you to have the appropriate expertise. Ultimately, the conversion process can be quite time-consuming and tricky, and you need to think about how you want your linked datasets to look pre-ontology design, not post. You also need to remember our old friend garbage in and garbage out. If you have an incomplete, messy, inconsistent data set, then just blanket converting it into linked data isn't going to make it better, unless through that conversion you are planning to iron out the issues of inconsistencies, etc. One of the big issues of data lies in the collection process. There are tons of data sets out there with missing data that use inconsistent units and schemas or just don't make sense in places, and this needs to be addressed as well. So just to sum up with some final thoughts, the semantic web is a socio-technical phenomenon. It requires a human effort just as much as the technological ones. It requires people to take the time to create the ontologies, to help progress the field, and to adopt the use of these technologies. And as with any technology, thought needs to be given to how best to implement it. As demonstrated in my PhD research, whilst there is a need for knowledge management and semantic tagging within scientific research, the solution isn't as simple as just setting up a system to do this. We need to understand how to do this in a way that is actually useful, and we need to think about the best times and places to use these technologies. And just a final quote to leave you with. Given the nature of our network, I know that many of you will work with AI, and I firmly believe that AI needs semantics. And to that end, I would argue, to the well-organized linked data set, AI is but the next great adventure. So just to finish up, here are some useful resources for using semantic web technologies in chemistry. There are many ontologies. There are the Royal Society of Chemistry ontologies, which I imagine Colin might mention in his talk, and I've noted a few of the very popular ontologies in chemistry and drug discovery. There are also several repositories of ontologies, and these allow you to search for relevant ontologies and also provide a place for you to deposit any ontology that you might create. I want to specifically talk about the Obo Foundry here, which I mentioned earlier. So they are noted down under ontology repositories. And the reason I want to talk about them is because they have defined standards for their ontologies. They have built upper level ontologies for ontologies to inherit and defined a relationship ontology to specify how a relationship should work. This is a really great initiative to create consistent ontologies around a specific domain. I've also noted several knowledge bases of richly semantically annotated data that can be used in the chemical and biological sciences. There are also many general semantic web resources out there that are useful for any domain. There's Dublin Core that is used to describe data sets. There is SCOS, Simple Knowledge Organizational System. This is really useful for organizing your hierarchies. Anyone who is familiar with either ontologies or indeed just plain old object-oriented programming knows that often hierarchies can be established with classes and subclasses. However, you don't always want to define a hierarchy in that way. Something can be embedded in a hierarchy without necessarily being a subtype of something else. And that's why being able to define things as broader and narrower concepts is really useful. It also enables you to describe how similar certain things are with different levels of matches. So if you wanted to say that one term is close to another but isn't exactly the same, you can also do this with SCOS. We have DBpedia, which is a crowdsourced effort to extract structured data from Wikipedia. And finally, we have schema.org, which is an ontology community where ontologies are collaboratively developed. I've also added some links to the linked data conversion tools that I mentioned earlier. So a link to the RTRML mapping language and the library I found most useful to implement it, and links to linked Open Data Refine and WebKarma. Naturally, here is a shameless plug to our publications, which explore what I've talked about in the projects in much more detail. And I just wanted to end on some acknowledgements. I've worked with a lot of great people on these different projects. Particular shout outs to Professor Jeremy Frey and Dr. Nicholas Gibbons, who are my PhD supervisors, and seemingly that wasn't enough to put them off, as Jeremy is now my boss on the AI3SD network, and Nick and I still work together on other projects. And of course to my work wife, Nicola Knight, who runs PSDS and who did a lot of the underlying work for Talk to Lab, and generally keeps me sane and swoops in whenever we need any help in AI3SD or other ongoing projects. So thank you very much for listening, and I'd be happy to take questions.